Great, thanks Austin for being here. I just want to say, once we were talking a little bit, but thanks again everyone for coming to this talk. A couple of things, please eat all the snacks in the middle of the table. It's more than we should have for this size, but I also don't want to take anything home, so please feel free. And then, besides that, and this is a different setting than we normally have for these talks, we usually across the hall, but I actually think it's good for the kind of talk that we like to have in the series, so please feel free, I'm not offending you, please feel free to interrupt Austin with as many questions as you'd like. We decided to have a conversation here about this topic. So once again, Austin is a PhD student finishing soon in the Applied Physics Department, working on machine learning in the development of batteries. And so just join me in welcoming Austin.
Well, thank you, and thanks again for your patience. I apologize for running late. I'm sure you all saw the abstract, and we were talking about battery materials and how machine learning can sort of assist us in furthering the development of batteries to meet our energy and climate goals. So I'm a firm believer in starting off talks with a joke. I don't know if you guys think this is as funny as I did. So Robin says the Batmobile won't start. Batman says check the battery, and Robin says what's a theory? Because Batman puts bat in front of everything. All right. Took me a while to get it, so sorry. Okay, so lithium-ion batteries. I'm sure everyone in this room is very aware of how much innovation they've enabled, especially within the last few years. These are sort of just a few of the domains where we've seen huge amounts of innovation through increases in energy density and decreases in cost, and increases in reliability in energy storage technology that have come about through lithium-ion batteries in general, but sort of lithium-ion recently has been a huge driver. Automotive is about a third-ish of our energy consumption in the U.S., and so these actually.
It's an anti-reflection coating.
Oh, is it?
Yeah.
Okay. Let's use it for we'll use some of that. Thank you for preventing that embarrassment. These two, this is both transportation, that's about a third of the energy use, and then of course, energy on the grid is the remainder. So batteries touch basically can touch basically every aspect of energy in this country. It's also no secret that today's lithium-ion batteries are not great. You've probably seen there's been major issues with safety with batteries, with whether it's Boeing's or Tesla's or Samsung's. There's been a lot of battery fires. What we'd like to see is that safety must be unquestioned in these devices. There's also still problems with energy density. So this is the amount of energy you can store per size, per mass or per volume. This has certainly improved over the years. The Department of Energy is pouring huge amounts of money into getting lithium-ion batteries about 2 to 3 times above where they are now. But if we want to start thinking about heavy transportation like aviation, you got to think about at least 10x, and just to start thinking about it to make it cost-effective or realistic, I should say, you got to get much higher than 10x. Cost is another thing that's really improved lately in the last few years. But if we want a Tesla to be cost competitive with a Honda Civic, we have to have at least the cost of the batteries come down to half of what it is now. And then of course cycle life is the number of cycles you can get on the battery before it dies. It's kind of hard to define exactly what a useful cycle life is because every application is different, but for everyone that owns a cell phone, you know that it's if you have the phone last 5 years rather than 1 year because of the battery, that's always preferable. So these are some of the axes on which we want to improve battery technology. So you could ask the question, well, how do we improve battery technology? What are the different approaches that we can use? So a battery is essentially 3 components. We have an anode and a cathode. These are the two metal terminals that you hook something up to. Excuse me. And then you have the electrolyte in between. So the electrodes, the anode and cathode, are typically metallic materials. And then the electrolyte is the material that separates those two. And the two main criteria are that it has to enable the flow of ions back and forth. In a lithium-ion battery, it's lithium. It has to inhibit the flow of electrons because we want to force electrons out of the battery into this external circuit. So the electrolyte is a really interesting part of the battery. There's certainly a lot of work on the electrodes, but the electrolyte is also very interesting because in today's lithium-ion batteries, like the one in this laptop or your phone, this electrolyte is an organic solvent. So think of, basically a solution of long carbon chains. We can't use aqueous solutions because lithium reacts with water, so we have to use these organic things. And if you know anything about organic solvents, they're very volatile and they're very flammable. These things like hairspray and all these different solvents that we know of are all super flammable. Electrolytes are no different. And so that, these electrolytes are, they're flammable, so there's the safety issue. They're highly reactive, which means that if you put too high of a voltage across these things, then they can start to break down. Excuse me. So that kind of limits the voltage you can have on your battery. You don't want to put 10 volts across these electrolytes. They also don't suppress dendrites, which is dendrite growth is one of the main drivers of battery, sort of early battery death. Which is where you have basically lithium starts to sort of grow from one electrode to the next. And these liquid electrolytes do nothing to inhibit that. So what our work is focused on is can we replace that liquid electrolyte with a solid material that will do the same job without any of these major drawbacks. So instead of a battery being two metal terminals with in a lead acid battery you have sulfuric acid in between, think now about just 3 solid components, one sandwiched on top of the other, and we're getting the same amount of energy, etc., out of it. And why solids are preferable is because solids are generally much more stable. They're less reactive than these organic solvents. They're not as flammable, and they can also suppress this dendritic growth. So if we go back to our original 4 axes of improvement for battery technology, solid electrolytes can really touch all of these, and they can really drive major improvements. Is there some water around?
Yeah.
That'd be great, thank you. Excuse me. So all of this is to convince you of that solid state batteries are a really interesting technology, and really what it comes down to is the materials. It's we need to discover some new materials. This is not really a problem of kind of tweaking the existing technology, for example, what you might do with increasing the mileage and efficiency of a car. You can kind of take the materials you already have, you just cast them in a different way, you increase the aerodynamic properties. This is really, we have to discover something kind of out of thin air with beneficial properties. So it comes down to the heart of basically scientific discovery as an idea. Now the challenge is, you could ask, well, why haven't we figured this out already? It's not because we haven't been trying. So these solid-state electrolyte materials have been on people's minds for about the last 40 years or so. And there's been, the initial work was kicked off around the 70s. People have been sort of searching ever since then with, unfortunately, not a whole lot of good results. So this is one of the first papers I read when I started my PhD. This is a review from 1976 talking about the properties of these lithium-ion conducting materials. And then 35 years later, there's one new material that's discovered, and it's a paper in Nature. Right, so that gives you a sense of kind of how rare these materials are, how hard they are to find. And you can ask, well, why are they so hard to find? Well, because these materials have to satisfy several criteria at once, and it's oftentimes basically a trial and error kind of process. So this chart here on the left shows this is just 8 of the, you could argue there's more requirements for individual materials for them to really work in these battery applications. You want to essentially maximize all of these axes at once. There you have 3 of the best materials, which you can see are good on some axes and are sort of bad on others. So if you're selecting materials at random and you're hoping that you can cross off 8 boxes at once, you can see that's a very difficult optimization to do.
So all the materials, you prefer lithium over anything else though?
So we've limited ourselves to lithium. There are certainly promising alternative chemistries, sodium, magnesium, all that sort of stuff. That's going to become, I think, increasingly promising and important going forward. But our attitude has sort of been, lithium is kind of the most ready to go. So let's try to focus on that first. Any other questions? And again, please feel free to interrupt at any time.
So lithium is the most ready to go because there's been the most work on it in the past.
Right. Yeah. So there's, the discovery of lithium-ion battery was sort of late 80s, early 90s. So it's been worked on. It's relatively young as a technology, but it's been worked on far more than, say, the sodium-ion batteries, where people have only been thinking about it for the last couple of years or so. And then there certainly are other battery chemistries, like lead acid, for example. Thank you. Lead acid in cars, but the energy density, the other properties are far lower. So lithium is promising for a number of reasons. Now, if we want to do a sort of brute force search for these materials, let's say we want to just get through every material we know of, well, how long is that going to take? Well, let's say it takes you about 3 days to evaluate a candidate. This is actually a pretty generous estimate. Whether you're doing simulations or experiments to examine these materials, typically what I've seen is that it takes you gotta kind of give yourself several weeks to get it right. If we say 3 days per candidate, there's 12,000 known candidates. That's 100 years right there. That's one heck of a PhD. And if you consider, really material space is sort of infinite because you can always tweak compositions slightly, then, immediately this goes to basically infinity. And so we don't want to just kind of, blindly start sampling materials. We want to really kind of reformulate the way that we think about this. Because, we don't have a whole lot of time to waste. The energy and climate challenges that we face are pretty significant. So our alternative approach is to use machine learning to seek a rapidly computable model that will change the way that we do this. So that's sort of the motivation for us. That's hopefully we've convinced you that energy storage is really important, and these batteries are really important. And the next question is, okay, well, let's think about this idea of scientific discovery, even without thinking about batteries in particular. Most people, most scientists will sort of begrudgingly admit that this is true. Scientific discovery is often very, very serendipitous. There's this great scene from 2001: Space Odyssey, where I don't know if you guys have seen this, where the ape starts hitting things with the bone and realizes that, hey, this is a pretty good material that I can use to accomplish my means. I suspect that's how the Stone Age started. It was just they tried a bunch of stuff until they found that rocks were pretty good tools. And of course, penicillin is a great example of a chance discovery, where Fleming had left his petri dish open. I think he went on vacation or something, and then he came back and some mold had gotten into the petri dish, and he realized that, hey, penicillin got in here and it killed all the bacteria. That was a pretty lucky discovery for us. Thomas Edison also engaged in some sort of serendipitous discovery. He sampled, I think it was, how many was it? I want to say it was about 10,000 different, he tried 10,000 different things before he found that this carbon filament actually lit up when he put it under voltage. So he's just trying things at random. And even in the upper right, that's meant to sort of signify the material searches of the present day. There's still a whole lot of trial and error that's going on. And we've invented these methods, for example, computational methods, like our group has employed, where you can essentially do what Edison did. You can try out a million different things, but you can do it in a computer, which means that there's far less sort of human involvement, but it's still trial and error. It's we'll try it. If it doesn't work, then we just try the next thing. And so that's kind of been the history of materials discovery, I think, to now. And we're trying to think of some way that we can kind of get around that. So I think there's basically sort of three elements to the process of scientific discovery. The first one is idea selection. So, hey, I'm going to look at this material because I think it's interesting. The second one is, now that I know that I want this material, how do I do it? Do I put it in a spectrometer? Do I put it under voltage and measure the impedance? All of these things. And then finally, confirmation of whether you're right. And this evaluation step, I think, is very much overemphasized in scientific education. I don't think graduate students should be leaving graduate school only knowing how to operate a piece of equipment, right? We should be thinking about sort of being critical in how we apply that equipment. And so I think the first part, this idea selection, is a really interesting kind of complement to that problem that doesn't get enough love. Why should I look at this versus why should I look at that? And so the way I kind of think about this is in a way, you're sort of turning with these machine learning approaches, you can kind of turn the scientific method on its head. So we know that data analysis is, that's a central part of the scientific method. And in the conventional version of the scientific method, that sort of happens at the bottom. So you propose a hypothesis, you say, okay, I think material X works well. You go out and say, this is what I need to measure to confirm that. And then you go make the experiment, you look at the data, and then you kind of come back and you reformulate your hypothesis, you kind of look at the next thing. Now, data-driven method, you're flipping this upside down, and the data analysis is actually happening first. So you're saying, okay, I don't want to assume anything about which materials are good and which ones are bad. I want to start by just getting a whole bunch of data on materials that are good and materials that are bad. I'm not going to make any kind of, not discriminating between any materials. And then through these machine learning algorithms, you can identify sort of what are the interesting signatures of those materials. And then those signatures can actually tell you, this is why this one worked, and this is why this one didn't. And so it's sort of, you're pulling scientific information out of the data. And I think there's an interesting analogy here to, everyone knows that the toddler doesn't touch the hot oven. This is basically a child who knows absolutely zero about thermodynamics in terms of the laws of entropy and heat flows from hot to cold and the entropy of the universe always increases. He will learn those rules very quickly when he touches the hot stove and says that hurts, and then when he touches the cold stove and says that doesn't, right? There's a whole host of very complicated scientific processes that are happening in terms of how the stove got hot, what happens when it touches his finger, how his body physiologically responds to that. But the important that's all kind of details that we don't care about. The outcome of that experiment can be interpreted very quickly from just looking at the output data rather than trying to model this entire system, atom by atom. So if we come back to our problem in materials discovery, this is how those two different methods would look. So the first one we'll call the conventional approach. Let's say I have this material, I think it's going to be a great battery material. We start with the positions of the atoms, we compute all the forces, we move it, we simulate it as we go forward in time, and then we measure these quantities, and then we say, okay, this is the lithium conductivity of this material. So we're invoking physics at all these steps. That's what takes us 100 years if we want to get through these 12,000 materials. Now, in a data-driven approach, we're saying, okay, forget about solving the Schrodinger equation. Give me a whole bunch of examples of good materials and a bunch of examples of bad materials. We know that the sort of physics is tied up in these atomic positions and arrangements. What I'm going to do is I'm going to train an algorithm to say, okay, based on what you've shown me, this new material looks more like those good ones or looks more like those bad ones. So we're circumventing this entire step of computing things from first principles. In a way, this is sort of like an analogy in machine learning would be it's very difficult to tell a computer program what a cat looks like or what anything looks like. But if you train an image recognition algorithm, you don't have to say, okay, a cat has whiskers, it has feet that might look like this, or you just say this is a cat, this is not a cat, and those patterns are sort of automatically learned rather than all explicitly stated from first principles. So again, this I don't want to belabor the point, but this machine learning approach allows us to hopefully do basically materials discovery in a way that's more efficient than trial and error by being smart with the data that we have. So before I jump into the next stage here, any questions, any thoughts?
Where are you getting your data sets?
It's a great question. So that's actually the next slide. So there are, so in materials generally, there's a new push to centralize a lot of this data. And so for some properties, you can go online and you can get maybe 1,000 band gaps of materials. Other properties, for example, in this case, we're looking at ionic conductivity, the ability to conduct lithium back and forth. There's no databases, and so this requires really difficult, scanning through the literature, asking other groups for data. It's a pretty painful process.
It's the same problem with cancer research or any other stuff. Where do you get the data?
Exactly.
And, can you replicate it? And is it good data or not?
Right. Any other questions, any thoughts? All right. So we'll jump into the work that's done here. So we went to the literature. When I say we, I mean me as a fresh-faced PhD student. Went through the literature looking for examples of these solid electrolyte materials. Ones that worked and ones that didn't. Our criteria was, they had to be measured experimentally at room temperature. They had to have known structures that were characterized, and they had to, belong to this class of crystalline inorganic materials. So we didn't look at, other things like polymers, for example. So we found, 40 measurements. I would say the number of materials, there's probably more than we missed, but I would say the number of materials that have been reported probably doesn't exceed like 100. Although there have been more and more published in the last few years. And then our job is, okay, so for these 40 materials, we have basically good materials and we have bad materials. Can we find some kind of signature that allows us to, without knowing what these labels would be, to differentiate between the two? So we went through and we extracted these 20 what we call features or hypotheses, basically 20 pieces of information about each material, which might have some bearing on conductivity. And so these are all, for each one of these features, this is basically one number. So, volume per atom is going to be different for all of these materials. Most of these were proposed or sort of suggested in the literature as candidate, descriptors for establishing whether something is a good conductor or not. So we know that there's at least some kind of wisdom built in from the get-go. So we computed these 20 for all 40 materials. And the first question was, okay, well, are any of these 20 the silver bullet? Because if they are, then we're done right away. So we measured these correlation coefficients, which is, how well do they describe that conductivity data? And we found that basically, among these 20, there was no real strong correlation. So these 20 in themselves, or individually, can't really describe this phenomenon that we're looking for. The hope is, and this is not obvious before you do it, the hope is if you have some sort of clever way of combining these criteria, then you can actually get some more predictive power. And there's a general rule in machine learning that says if you combine a bunch of what we call weak limiters or features that have low correlation, if you combine them together, you can actually get a resulting model that's a much stronger predictor than those individually. So that's basically our hope for this case.
What do you mean when you say combine them?
So basically the question is, can you, instead of just saying, okay, this is, for example, like volume per atom, I just have to compute this and this is my answer. A simple combination would be, volume per atom plus standard deviation in lithium neighbor count, right? So you have to consider two at once. And then if one of them is, maybe both of them need to be large, and then it's a yes. If one of them is large, one of them is small, then that's a no, right? So you gotta have some way of sort of considering multiple variables at once. Of course, there's a zillion different ways you can do that. You can do like linear models, you can do non-linear models, you can do all kinds of things. And that's where it sort of gets subjective in terms of just, you got to try a lot of things. But that's a great lead into the next slide, which is that we decided to use what's called a logistic regression classifier. So what that looks like is we take these 20 hypotheses, we take these 40 data points, and then we find the subset of those 20. So it might be only one of them, there might be all 20 of them, there might be 5 of them, which you can put into this model and gives you the best predictive power. So this theta x, this is just a linear combination of those. How many x's do you need? Do you need 2, do you need 3, do you need 4? That's where these machine learning metrics can come in. So this is one way of sort of combining those features into a multivariate predictor. Again, there's a lot of different ways to do it. We did it this way because we have a small data set, and these sorts of models are better suited to small data. When you have a large data set, that's when you can start thinking about, neural networks, for example, are the big thing that everyone's using now. But there's a million other different models, as we said. So this is sort of one place where our kind of human bias can come in because we're constraining it to this form. But the hope is that if you kind of look at enough different ways of modeling these things, that you can actually find the one that's the most predictive. So there's a whole really interesting kind of process that goes on in terms of how you find the features, the subset of those 20, and the regression coefficients that go into the model. I can get into that if we want to, but I think it's easiest to just sort of describe the process is basically, this is all automated, and so you can actually build every possible model out of those 20 features, which is 2 to the 20, so there's about 1 million different models that you could imagine just within this logistic regression form. For each one of them, you can fit it to the data, you can see how predictive it is, and then you can select the most predictive one of those 1 million different models. And so that there's another, this is a whole other field in terms of how you narrow down the feature space to the features that you want. A bunch of different ways to do that. For us, one of the advantages of the small data set is you can actually just build all the different models, and you can say, if I go with this model, what error do I expect versus this one? And so the model that we settled on is this 5 of 20 feature data set model, where we have these 5 features, which are all easily calculated from these structures. And then what you do, for each material, you compute those 5 features, you plug it into this equation. You have the regression coefficients that are found from basically the fit of the line. And then you plug that into this logistic regression form down here. Basically, if this expression, this long expression here, evaluates to greater than 0, that means that there's a better chance that it is a good ion conductor than not. And if this evaluates to below 0, you can say it's more likely to be a bad conductor. So this is basically just telling you, kind of, given the good and bad examples you've shown me, this is more likely to be good or to be bad. And the really valuable insight from this, or the value add from this, is that whereas it took us at least a week or several weeks to compute a connectivity prediction with density functional theory, or these physics-based models I was describing earlier, this model is so fast that we can evaluate it in less than a second. And so that was our motivation from the beginning, is let's find something that's orders of magnitude faster. And none of this stuff requires us to solve the Schrodinger equation, to do anything involving kind of fundamental physics. And so it's super quick to evaluate it. We're certainly, we're probably missing out on some of the important information, and so we think that the accuracy is not going to be as high as if we're doing this really rigorously. But it's the only way that we can build something fast enough to go through 12,000 candidate materials. So that was what we did, and we used this to scan through these 12,000 candidates. From the 12,000, we identified the top 21 that were most promising according to this model. We computed a whole bunch of other properties about these materials to confirm that they were, for example, not electron conductors, as we mentioned earlier. So there were sort of other screening steps involved in this to compute. We also computed sort of cost estimates for, dollars per square meter. This is an indicator of the Earth abundance of the materials that are involved. So we're trying to kind of optimize on a lot of different axes. but we got this list of 12,000 down to 20. So we took the route that I like to call publish and pray, which is where you put these predictions out there in literature, or you publish them in a paper. You have no idea if your predictions are right, but you pray that they are, or else you look like an idiot. But I think that's an important and kind of subtle step in these data-driven or modeling approaches, because if I think if you make a bunch of predictions and then you confirm a bunch of predictions at the same time, it can kind of get sort of unclear if the results are contrived, or if you're changing your model based on the new data that you have. This is really based on the original data. So our philosophy on this has just been take the model, publish it, go validate the model, publish that as a different work, and be very clear about sort of what was trained with what, and what the expectations are in that sense. So the next question then naturally is, okay, well, you screen these materials down based on what you think is most promising. Are those predictions actually right? So that was the next part of this, which is where we really extensively went through and we did those types of simulations that take weeks to do. We did some experiments as well. But 20 is a much more tractable number to do that on than 12,000. So what we found was that, we do these physics-based simulations. Essentially, we take these materials, we set them at high temperature, and we simulate what happens to these temperatures. So the atoms are all jostling around. What we're looking for is we want the lithium atoms to be moving. We want everything else to kind of stay where it is, but we want lithium to be very mobile. And so the way that we determine if it's a good lithium-ion conducting material is we track basically how far those lithium atoms have wandered in time. And that's what we plotted here. So the slope of these curves, so each curve is for a different material, and it tells you something about how quickly lithium is diffusing. The slope of these curves tells you they're proportional to this conductivity, the original metric we want. So we want things like this red curve where lithium is really diffusing quickly. We don't want things like this down here. And so what we found is that we had about 4 materials that are in this kind of top tier of really excellent conductors. These are like on par with the best known materials out there. And then we had about another 4 or 5 or so that were in this kind of middle tier. These are things that are still very good conductors and still be useful in batteries, but are not like world record-breaking materials by any means. And then we had about half the materials that we never saw any diffusion. So these were basically false predictions by the model. So all in all, the model gave us correct predictions about 50% of the time. So how do you interpret 50%? In most things, in most aspects of science, if you're right 50% of the time, that's a terrible accuracy. But again, we're trying to predict something based on a small data set and something that is exceedingly rare. So these, like I was saying, these lithium-ion conducting materials, people have been working on this for 40 years. So maybe 50% is pretty good. Well, the way that we actually say something about how well this approach is done is we want to know basically, if we were doing trial and error, which is what we would be doing otherwise, what kind of success rate would we get? And how does that compare to 50%? That is the question. You can't really answer that without doing trial and error. So we thought, okay, well, let's just do some trial and error and let's see what happens. So we took these materials that the machine learning algorithm told us to simulate. We simulated them. How you sort of count success is kind of there's some subtleties in here in terms of statistics. We'll say it's between 35 to 50%. There's it's a number we're getting into, but there's other things to consider. And then we just started randomly selecting materials from this pool. We're actually surprised to see that we got some decent ion conduction about 10% of the time. That's probably higher than it would be experimentally. There are certain things that in these simulations where you can sort of get inflated conductivity numbers. In real life, I think that's probably a little bit high, but nonetheless, you compare 35% to 10%, we see that's a 3 to 4 times improvement in the number of discoveries per time. And what our results look like if this is a histogram of bad, decent, and really great lithium-ion conducting materials. The gray is the distribution you get at random, and the red is the distribution you get when you listen to this machine learned model. So you see the number of bad materials is cut basically in half, and the number of really great materials, it goes up by like 3 or 4 times from this random case. So the takeaway here is that this model, I think it's worth emphasizing, this model was trained on only 40 data points again. So this is a very small data problem. By the standards of Google or Facebook, this is basically no data. This is 0.0 data points. But from just these 40 data points, we're sort of being careful about how we build these models and how we incorporate the sort of pre-existing knowledge about factors that influence conductivity. Actually, get a 3x improvement over random trial and error guesswork. So, did you have a question?
Yeah, no, just,
Okay.
yeah, I was gonna say in 100th of the time.
Right, exactly. So you're preempting my slides. Yeah, that's great. So I showed this slide a couple months ago, and there was a scientist in the audience who made a very good point, which was, well, not every scientist is guessing at random. Right? It's like, okay, that's fair. Can we do a Gary Kasparov versus Deep Blue kind of situation where we can put the expert wisdom up against the machine rather than just the kind of drawing materials at random? So, that was the next thing that we did. We pulled a bunch of PhD students in the material science department. It was hard to get professors to do this because they didn't want to, I think they were afraid that they would not beat the machine, I think, or they didn't trust it or something, but the PhD students were game. So we pulled about 10 PhD students. We randomly selected this list of materials, and we gave them all the information that the machine learning algorithm would have. So everything relating to structure, the compositions, the symmetries of these materials, all that sort of stuff. And we said, okay, identify from this list, identify the materials that you think are these extremely good lithium-ion conductors that conduct basically as good as liquids. And then we give the same list to the machine learning algorithm. And what we found is, so here's the axis of accuracy on the x-axis and speed on the y-axis. So this is where your point about speed comes in. So if you were to be guessing at random from this list, you would be on this random guessing baseline, which is this dotted gray line, which is about 10% F1 score, which is a metric for accuracy. The PhD students beat that by a factor of 2. So that was great. That's a victory for PhD students. We're not guessing at random. The machine learning algorithm, the logistic regression trained on 40 examples, roughly doubled the score of the PhD students. And the great thing was it did it in a fraction of the time. So we have this Y scale is this log scale for time. So number of predictions per second. So you want to be higher up here. The PhD students took on the order of about a minute to make each prediction. The trained model, of course, was taking like a microsecond to get through each one of these. So we beat the PhD students on speed and on accuracy. And then as a reference, we have these physics-based models, which are super accurate, but are incredibly slow. These are the ones that take us weeks to evaluate. So I think this really shows the sort of value of these machine learning algorithms in material science. It's very valuable when you need to sort of beat, you don't need to be 100% accurate, but you need to beat basically this like sort of trial and error game, and you need to do it much more quickly than the existing methods allow you to do. So with that, we still have, let's see, we have about 15 minutes.
No, we actually end.
Do we end soon?
Well, around 5:20, but if people are free to stay
Okay.
longer, then we're happy.
Okay.
We're happy to host.
Great. Well, I would just leave you with this point, which is, we're really excited about the fact that we have this 40 data point model that drove 3x improvement, and we start thinking about what we can do with hundreds or thousands of data points. And fortunately, there's these new efforts to aggregate this materials data in databases, which is great. Our group has, since this sort of original proof of concept study, we've expanded these approaches into attacking multiple aspects of battery materials at once, getting into electrodes as well. And I think it's eventually we'll sort of get to a point where we can design entire battery chemistries without having to do single experiments, where we can optimize all these different components at once. And maybe we'll have to do some experiments, but we can do them 10 times faster and more targeted than we would be doing originally. So I think the future is very bright for the role of machine learning in materials problems and in batteries specifically. Hopefully I've convinced you that as well. And thank you for your attention, and love to follow up with any questions that you guys might have. Yeah.
What's your biggest barrier to accuracy right now, to improved accuracy? Is it a data set, or is it your formula? Like, is there room for improvement there?
I think, it's a good question. I think it's just the size of data. There's, it's hard to be really accurate on small data sets.
Mm-hmm.
If you have, I would say the more data you have, the less that you need to know about the problem in order to solve it. So if we could get 1 million data points, then you could just plug it into a neural network and not, it would probably just solve it for you.
Yeah.
And we're trying to work on that a little bit. So we have an initiative to, basically get people to sort of send us their data. Yeah, exactly. Because there's so much data that's in, in lab notebooks that gets thrown in, a cabinet and then you never see it again. So.
Thank you.
Yeah. Yeah.
Well, I think in terms of your small data, maybe if you can try do bootstrapping, that could help. You don't need to get more data.
Yeah.
If you can just bootstrap it and then see if your model is going to be really improved. It doesn't have to restrict to 40 data point.
Yeah, that's true. Yeah, and we are doing some sort of Bayesian optimization techniques to target the way that we gather new data in a way that will maximally improve the model. But yeah, there's a lot of exciting ways to think about that.
What happens? So I don't know that much about batteries, but like my phone has a battery and the materials in that. What happens if you plug the information about my phone's battery into the model that you've created? Like, do you think will it say it's a pretty good conductor or not?
That's a good question. So the phone batteries that we have these liquid electrolytes, and the screening that we've done so far is based on solids. But so two things. I mean, so we're thinking about moving into screening of liquid electrolytes as well, because they're, the sort of liquid electrolyte industry is already set up, and so it's much easier to change the way you do that rather than having to change the whole chemistry. But we did look at some known solid electrolytes that have been, we weren't involved in the training of the model that people have since discovered. And we found that the model actually does a pretty good job in predicting some of those. So we put those in the original paper. I think that was kind of what helped convince the referees that this was real. It was like, it predicted this, and then, it turns out someone discovered it 2 years ago or something. So it tends to do pretty well.
Yeah. So you have the simulated part as like your ground truth data. How easily does that transfer over to the real world?
That's like the curse of being a theorist. It's like, and it depends who you ask. I think in general, it's the simulations for these sorts of properties. Simulations are pretty good. Or they reproduce experimental results pretty well. But the issue is that what you're simulating in these simulations can be very different, because you're simulating maybe 100 atoms at a time. And so you're looking really only at the bulk behavior of these materials. You don't have the edge effects of these materials. Oftentimes these are made in polycrystalline form, so it's a bunch of materials that are sort of smashed together, and then you get these voids that are not captured in the simulation. So usually the way that we think about it is, if you could grow a perfect, pristine single crystal, the simulation would be pretty good. But once you start to get other effects, then it can complicate it. So I would love to know, in general, how the two, what the correlation is between simulation and experiment in these cases, but in general, I would say it's a great sort of first tool to identify the best materials.
What other fields do you think that this approach could extend?
Yeah, so I think that's where it gets really exciting. I think any place where you have materials discovery is your big bottleneck. Thanks. Is really exciting. So I know people are thinking about this in terms of catalyst discovery. Actually, Jens Norskop's group here at Stanford is doing some of this. Interestingly enough, the sort of pharmaceutical chemistry world has been using techniques like this for a really long time. I think going back to the 90s. And but they never really percolated into the materials world until the last couple of years. So there's a fair amount of companies and research groups out there that will do this sort of machine learning driven aspect for drugs. But I think it's the possibilities are pretty exciting. There's a company called Citrine Informatics that came out of Stanford a couple of years ago, and they're using this in discovering new alloys for airplane structural materials and all kinds of stuff. So it's pretty generalized.
Have you looked at data from other domains that might be similar?
Other domains meaning other other kind of materials, or
yeah.
So we've been limited to batteries, but we've tried to sort of stay abreast of what other people are doing. I think the challenges are all fairly similar. It's all small data, but it's hopefully it's improving.
In such high value information, are there a lot of proprietary barriers to acquiring new data points?
Yeah, so the battery world is very interesting in that I think it's one of the few cases where industry is in some areas industry is really leading academia, but academia doesn't know it because everything's proprietary. So we sort of we'll go out and talk to companies and see if they're interested in sharing data. They sometimes have huge data sets, but it's almost always it's a no way because there's a lot of value tied up in that. So I've thought a lot about that kind of idea, making some sort of industrial sort of consortium model of. I think this was done in the semiconductor industry in the 90s, where everyone kind of sharing wisdom. I would love to see that with batteries, but there's just so much sensitivity around the data. I'm not sure exactly why, but it makes things tough.
Can the Department of Energy partner with sort of this technique of? So
the White House actually, I think this was the Obama administration, I think maybe around 2009 or 10, they launched the Materials Genome Initiative, which was a White House initiative to basically do this kind of centralized data gathering and all this stuff. They funded a whole bunch of projects, including the database that we use in this case. Unfortunately, as of 2017, that initiative is no longer there. But I think that hopefully there'll be some interest from the DOE and others in kind of extending that. So there certainly is momentum going that way.
Who's funding your work right now?
So I'm funded by the Tomcat Institute here at Stanford. But we also have, let's see, who else do we have funding from? We have some funding from Toyota as well that have been interested in this approach. A few other people. I think industry is kind of in this wait and see kind of attitude, where they want to see the results at the university before they really start adopting it in-house.
Do you know if anybody else somewhere, I know you said it's very secretive, but do you know if anyone else is doing the same kind of thing and competing with you?
So, yeah, that's a great question. I've been trying to figure that out. I think I would be very surprised if Tesla was not. Tesla is very hard to get information out of. Mm-hmm. But I have good reason to think that they're doing this. But I don't know about anyone else. I've seen a fair amount of skepticism. Like what you're saying about Toyota, I think people are kind of like, you show us that it works first before we do it. But But, the difficulty is, it's sort of unproven and it's a very different way of doing things. And I think there's just a lot of sort of entrenched thinking that can be hard to overcome in the industry.
Makes sense.
Isn't Tesla trying to get away or seeing if they can use less lithium?
No, I don't know.
I suppose that's one of the big
Yeah,
issues with their supply chain.
yeah.
Is, the raw materials are tough to get.
Yeah, I know that they, basically all of the lithium in the world is in sort of geopolitically difficult regions. And so I know that they were looking at potentially trying to find ways to source that from within the US. I've heard that there was maybe some progress on this in Nevada, that there was some lithium deposits that have been discovered recently, but I don't remember much more than that. But I haven't heard anything about them going beyond lithium.
Great, well, thanks again, Austin.
Yeah.